Okay, so like I said, the first couple sections here, the first section is like roots, so it'd be like square root, cube root, that kind of thing. So there's a bunch of definitions and stuff, but basically you just have to know that like a root of something is like undoing a power. So like if you had like, you know, something to the power of a third, the opposite of a power of a third would be like the cubed root of whatever that is. So those are opposites or inverses of each other, right? And then in one of these formulas, I think it's this one here, the exponent theorem, it basically just says if you've got something like this where it's like the cubed root of x, that's the same as x to the 1/3, because not all the calculators have an option for like cubed root or fourth root or 10th root of something. So you can always just do it as whatever your base is to the power of that value, and that will kick out your answer. So let's go, I got you guys the example sheets, right? Okay, so let's hammer out that first one there, and then we'll kind of talk to the next thing. So the first one here, it wants us to evaluate these without a calculator, which will be helpful with the log stuff, kind of working stuff backwards. So evaluate it. So we've got, what is it, 1,000,000 there to the third. So that would mean like the cubed root of 1,000,000. So what I would be thinking there is basically what value to the power of 3 is going to give me 1,000,000 is kind of my thought process. What you can do with these, what I do with my algebra 2 kids, is I make like a factor tree and kind of break this stuff down. In this case though, this one's actually not too bad to kind of break down because of all of these zeros here. Any thoughts on what number we could take multiplied out 3 times and get this number? My thought would be is if there's 6 zeros there, that would be like a group of zeros, group of zeros, group of zeros. Well, if it's zeros there and a 1, isn't that 100? So if I took 100 times another 100 times another 100, wouldn't that give me 6 zeros? It would, right? So to kind of undo this here, it would be like 100 to the third would give us that. So that means that the cubed root of that, or to the power of 1/3, would be 100. Next one there. When they give us a decimal value like this, a lot of times I like to turn it into a fraction because it's actually easier to do the roots of fractions. So like if I had that 0.09 to the 1/2, to turn this into a fraction, it's kind of similar to what we were doing at the end of last chapter where it's got like 2 positions behind the decimal. So that would mean that it would be like 9 over 2 positions would be like 100. And then that to the power of a half. And then remembering back to like last year when you do this, if you've got a fraction to a power like this, you can actually split it up into the top and the bottom. So you could do like 9 to the power of a half and 100 to the power of a half. And remembering that power of a half is the same as like square root. So like what's the square root of 9? 3. And what's the square root of 100? 10. So it'd be the same as 3/10. And if you wanted to do it as a decimal, you could, you know, move it over and stuff, but that would be good enough. And then that last one there, I should have wrote this a little different. I'll do my C over here. Same thing. So we've got negative the 16 over 81 to the 1/4. So similar, when it's a fraction like that, you can just break it into its 2 parts. So you could do like negative, you know, you could do 16 to the 4th over 81 to the 4th. And 4th is a little bit harder to think about because you're thinking, okay, what number multiplied out 4 times would give me 16? If you don't know that like right off the top of your head, what I did with my Algebra 2 kids is I did like a little factor tree where I basically take 16 and then I go, okay, what could 16 multiply to? Well, things that multiply to 16 could be like 4 and 4, and then the 4s could go down to 2 and 2. And then what you're looking for is you break it down to like all of your prime values. I don't know how Kasich did this with you guys, but this is what I do with my kids. And then what I do is I'm like, okay, well here, if I had that 2 multiplied out 4 times, wouldn't that be like the 4th root of 16? Because it would be 4 times multiplied. So that would tell me my top there is the 2. And then if I just did the same thing with like the 81, so if I did 81 broken down, well, it would be 9 and 9. 9 would go to 3 and 3. That's all my prime stuff. So wouldn't 4 of the 3's multiplied together be the 81? Yeah, so then working that backwards, that would mean the fourth root of 81 would be that 3 then. And you would just leave it like that. Okay, so again, hopefully you guys covered this stuff last year. I'm sure you did. But just a little recap on some of that stuff. Our next example here, we're going to use this exponential growth and decay formula. I'm going to have us label some stuff in the formula. That's why I've got kind of a space in there. So exponential growth and decay is like something increasing very rapidly or decreasing very rapidly. So here to label some stuff, our y is always going to be the ending amount, so the amount that gets kicked out. So I'm just going to label that ending amount. The a is going to be our starting amount. The b is our growth factor, so like how much it's increasing or decreasing by. And then that power of x there is always our time, so like how many years or whatever we're doing that for. So if they say something about figuring out like an annual growth or something, this is the formula we're going to use. And then to determine if it's like a growth problem or a decay problem, if they don't tell you, you just look at your growth factor. If your growth factor is bigger than 1, that means it's like going up. If your growth factor is between 0 and 1, it's not going to be negatives, but if it's a decimal value between 0 and 1, that would be decay, or it's like going down. So growth going up, decay going down. Okay, so we'll just use that formula for the next example then. So, where's my sheet? There it is. Okay, so we got in 1965, 12-ounce box of cereal of Corn Flakes cost 25 cents. In 2008, same 12-ounce box of cereal cost $2.99. What was the annual growth rate in the cost? So here we'd be thinking that we'd be using that formula, so like y is equal to the ab to the power of x. Our years there are going to be important, so that 2008 and then 1965, because that'll tell us like how long we're doing this. So to figure out how many years that is, I would just do like 2008 minus 1965 to figure out our years value. So I've got it, I think it's 43. Yeah. So 43, so that's going to go in for the x because that's our time. We're trying to figure out the growth factor, so we don't know what that b value is. So that'll just stay as that. The a stands for our starting amount. Well, our starting amount in 1965 was the 25 cents, right? So I'm going to do that as a decimal, 0.25 for 25 cents. And then our ending amount would be our value in 2008 because that's where we were stopping it at. So 2.99. And then we would just solve that just like a normal equation. So like I would get rid of my multiplication before I would do the power stuff. So to get rid of multiply by 0.25, divide by it. And if I do that, 299 divided by a quarter is 11.96 is equal to our b to the power of 43. And then kind of like we were talking about before, when we have powers, the opposite of the powers is the roots of it, right? So like if we had something squared, to get rid of it, we square root. Same thing happens here. So to get rid of a power of 43, we just do the 43rd root of it. So you could either do it as like root of 43 like that, or you could do it as like, this would be the same as like 11.96 to the power of 1 over 43 would be equal to our b, because that stuff would cancel. This would be one that you could use your calculator to get out. So that's why I do that one. So 11.96 to the power of, I think on the old ones you gotta do parentheses 1 divided by 43. The new ones will just raise it up so you don't have to do that. But I get some number there, and it's a gross number, but that's okay. So b is approximately equal to like 1.059-ish, something like that. And then when we're talking about this for growth rate, typically they want it as a percentage. Now what you have to think here with this is the 1 out front stands for like 100% of something. We just want the part that it's growing by. So what you would do in a case like this is you actually subtract this value by 1 and just have the 0.059, because the 1 is like the 100% that we've already got, and then the growth is just that decimal number. And then we know to turn a decimal to a percent, we just multiply by 100. So we go over 2 places there. So it'd be the same as about 5.9%. So if you get something like that, you just basically plug it into a formula and find in what you need. Okay. Looks like we're going to example 3 next. Ooh. This one's kind of gross. I think I'm actually going to skip this one. I can write it out later if you want the notes on it, but it's basically a long thing out, and I don't think it's going to be super relevant to us to know to move forward, so I think I'm going to skip this one. I can write it out on the note sheet if you want me to, so I'll scan it and stuff like I normally do, but to save us a little time here, I think I'm actually going to skip that one because it's a long process out, rationalizing the denominator and stuff, and I don't think it's super relevant to us, so let's just skip that one. I am going to fill in some extra things to our little note sheet here, though. So just again, some review on stuff when we've got like odd and even powers. So we know when we've got a graph and it's like an odd power, we get something that typically looks like that, right? Where it's like rotation symmetric, you know, one side's kind of going up, one side's going down. So that would be like a power of 3, 7, 9, that kind of thing. So what they want us to know from this stuff is if you've got some sort of k value here, like in the y spot that it was equal to, so like y was equal to just some random k here, wherever that's out on the graph, y equals is like a horizontal line. No matter where that is on the graph, if you draw a horizontal line across there, it's only ever going to cross it in one spot. So if you've got an odd power and you're looking for like what it's going to kick out, there's only going to be exactly one real solution to that, okay? It gets a little bit more complicated when it's the even ones, and again, this is stuff we've talked about before. When it's the even ones, we got to graph something like that. So pending what your k value is, whether it's positive, a 0, or a negative, you've got a different amount of solutions here. So like if your k was a positive value, so like somewhere up here, so like say that's your line and like it's like y is equal to, I'm going to label it as k1 just because there's going to be two different k's here. That's going to go with that one there. In a situation like that, we're going to have two solutions, right? Because it's going to hit that graph in two spots. If you have an equation where it was like your y was equal to 0, so kind of going across there, because our parabolas always hit that spot there at 0, 0, you would just have one solution in that case. So if that k value was 0, you just have one spot there. And then we talked about this before, like when it's a situation where it is like a negative number, basically you'd have kind of like a line going across here somewhere. That's not going to cross that graph at all. This is where like the imaginary number stuff comes into play. So that I'll just label that one as like K2. But that one would have no real solutions. It would have solutions, but they would be the imaginary ones. And if you remember before, we kind of talked through that kind of stuff. And I don't know how much of that you're going to need to know, but I just figured I'd throw it on there since it was part of it. And then there's a theorem that actually kind of goes along with that too. And again, I just copied what the book had for that theorem. But it kind of talks through that too, where if it's like a positive number, pending if it's an odd function or an even function, it tells you know how many answers you're going to have. And then the same if it's a negative number, how many answers you're going to have and that kind of thing. So this theorem kind of just goes along with that stuff. But like I said, I got it all typed out for you. Okay, so I think we basically just have that last example there. Yeah, so there is another formula thing here. We talked about this already though, where like if you've got a root of something, that's the same as like the power of 1 over whatever that root value is, which we talked about. So let's just hammer out that last example then. So here it says evaluate square root of negative 63 on a calculator for complex numbers and confirm that it's the result is the square root of negative 63. Here, our calculators, unless we change the settings around, you're not going to be able to type in like just square root of negative 63 and get a number. It's going to tell you that it's like not a real answer because we know it's going to be imaginary stuff when we do like the roots of negatives. So if they ask you a question like this, what I would do is I would just do the square root of 63, get what that number is, and then we know it just throws an I with it because we know like if we split this into like square root of negative 1 and square root of 63, we know that square root of negative 1 is just an I times whatever that square root of 63 was. And then again, they just want it approximately. So you would just put whatever this decimal number is, so like 7.937, something like that. And then you just throw the I with it. And then basically just to confirm that it is the square root of that, if you just took that value and multiplied it out, so like that decimal number, 7937I or whatever, and squared it, you should kick out a negative 63, because if we took this number and squared it, it would be like the opposite of what we just did. So it should get to be 63. And then do you guys remember what I squared is always equal to? Negative 1. So really it'd be like 63 times negative 1. which gives us that negative 63. So that's just confirming that that works for that. Like I said, hopefully most of that stuff's reviewed. That's why I didn't want to spend too much time on it. I'm going to do the same thing with the 9-2 notes too. Again, I've just got it all typed out for you, so you don't have to worry about writing down any theorems or anything. Again, it should be mostly review stuff. So this is just going to be like exponents of things and what we do when we have exponents. So like if you've got an exponent that's a fraction like this, the top number is always like the power and the bottom number is always the root, and that's kind of what they've got going in this first formula here. That if you've got something like that, you can just take it and put the top number as a power and the bottom number is just the fraction like the root. You can also do it the other way where you do the power first and then the root second. It doesn't matter. Let's just talk through all of these first and then do the examples. The other stuff that's important here is these are just the properties of the powers. So like if you do like a power of a power, you would just take whatever your powers are and you multiply them. So I'm just going to highlight all these little formulas here. This one, if you're taking two powers or two things with the same base and multiplying them with the powers, you add whatever those values are together. If you're dividing with the same base, you subtract the powers. If you've got a power on the outside and then two things multiplied on the inside, you can just take whatever that power is times the stuff on the inside, or not times it, but kind of like distributed to both of those things, and then you can do the same thing if it's division on that. So those are kind of the important things, and I think you guys are smart enough if you just look at those things, look at the examples, you can just figure it out from there. The other two important ones here, anytime you have a power of 0, no matter what the base is, it'll always kick out a 1. And then the other one there, this is the one that people sometimes forget. When you've got a power of a negative, what it does is it takes whatever your fraction is, and it does the reciprocal of it, or it flips it over. So that's kind of the important one there. Yeah, give me a sticky note already. Okay, so let's just hammer out these other examples here. So you have to flip a little bit to get to the 9-2 ones. Okay, so first one here, it wants us to evaluate this without a calculator. So what I would probably do on this is if I've got 100 to the power of 3 over 2, I would break this kind of like they did on this first theorem here into kind of two parts, where I break it into like a square root and I break it into a power of 3. So I would kind of switch this to like 100 to the power of a half and then to the power of 3. And the reason I do it that way is because square root of 100, we can easily do that, right? Square root of 100 would give us 10. So then that would simplify to 10 basically to the power of 3. And then 10 to the power of 3 is not bad to multiply, because just 10 times 10 would be 100, and then 100 times another 10 would be 1,000. It's just the amount of zeros. So it would just end up kicking out 1,000. This number 2 here is kind of a weird one. There's a formula in the book that kind of talks about this. It's probably just weird because I don't know anything about music and keys or anything like that. But there's a formula on page 570 if you have to do any questions on this. Basically what they've got is they've got like some value is equal to 1/2 to the power of something divided by 12. Whatever that top value is, that's how many keys above one note is compared to the other. So I'm just going to write a little note there that it's number of keys above. So like in our question here, it says the F that is 5 piano keys above. C sounds very good because of the ratio of lengths. It has something to do with the ratio of lengths of strings of, I don't know, some musical instrument. And basically all we're doing there is we're just taking and putting that 5 into that spot there because it's 5 above. So like our F would be equal to 1/2 to the power of 5 over 12. And then because it says we can just figure this out here, we can just do this as a decimal. It doesn't come out to be a nice number. So I would just do like 1/2 or 0.5 to the power of 5 divided by 12. And I get some sort of gross number. So like 0.749, something like that. And then what's weird about this question, it says they want you to figure it out as like a ratio. Well, a ratio is a fraction, and this isn't like a nice number as a fraction. So they just want you to say that it's approximately equal to 3/4. I don't really like that because technically it's not 3/4, but like this is approximately equal to like 0.75, which is 3/4. I don't know. I don't love that question, but in case they ask any questions like that, you're just putting the number into that power. Okay, next one here. Find a simple fraction or integer equivalent to that. So what I would do is I would take that 64 over 729 with the power of 4 over 3. And I would do the same thing as I did before, where I kind of break it into the groups. So I'm like, okay, well, I can do 64 to the power of a third, 64 to the power of a third, oops, not 64, 729, sorry, to the power of a third. Then whatever those values are, I could get to the power of 4. So again, what you're thinking when you're doing like a root of something, if they wanted you to do it out by hand, or like you didn't have your calculator for this portion of it, say it was like on a math test or something, they didn't give you a calculator, you just take 64 and you break it down and hope it comes out into even groups, like a group of 3. So like 64, we could go like 8 and 8, and then 8 could go down to like 2 and 4, 2 and 4. 2's are primes, so I circle those. 4 would go down to 2 and 2, 2 and 2. All of those are prime. So I would end up with 6 of those 2's being multiples. 2 for the last one. And I'm looking for like groups of 3 because it's the third root. So what you do is you go, okay, well that's a group of 3. That's a group of 3. So it would be 2 times the 2. So 4 would be the third root of 64. Because if I took 4 times 4, I get 16. 16 times 4 would give me to 64. So that top number would be 4. And then you could do the same with like your 729. Break that down. I didn't write it down what it would break to. Should be a multiple of 9, I think. Yeah, 9 and 81. 9 could go to 3 and 3. 81, 9 and 9. Kind of the same process. So 1, 2, 3, 4, 5, 6 of those again. So if I make my groups again, it would be like 3 of them there, 3 of them there. So 3 times 3 would give me 9. So like 4/9. And then I would do the powers of 4 for each of those. So basically you just multiply the 4 out 4 times. So it'd be like 4 and 4 is 16, another 16 would be whatever 16 squared is, which is 256. And then 9 to the 4th, well 9 and 9 is 81, and then if you did that again, another 81. 81 times 81 is 6,561. I wouldn't worry about, doing all that out by hand. You guys can kind of figure that out on your own if needed, but that's kind of how they want you to simplify it down, but like I said, you can use the calculator on some of that if needed. Number 4 is kind of weird because they want us to write this as a power of 3. So basically they want us to kind of change it where instead of it being like a 9 as the base, they want it to be like a 3 as the base, which is kind of silly. But what you could do is you could rewrite this. 9 is the same as 3 squared, right? So you could have this as 1 over 3 squared to get that base of 3, and then to the power of negative 2 fifths. So from our little notes page, if it's a power of a negative, what happens is your fraction basically flips over. So this would be the same as if we flipped it to 3 over 2 over 1, and we know we don't really need the 1 there. And then it would be to the power of 2 fifths, so basically the negative just takes that fraction and flips it. Then what you can do is powers of powers from our note sheet. You take the powers and you multiply them together. So if it's powers of powers here, it would be like 2 over 1 times 2 over 5. So like 2 over 1 times 2 over 5. We know when we multiply fractions, top times top, bottom times bottom. So that would be the same as like 4 fifths. So it would end up being the same as 3 to the power of 4 fifths. Again, that one's weird because why would they want you to switch it to a base of 3? But I don't know. They ask weird questions sometimes. Okay, last one here. Sphere has a diameter of d, volume of that equation there, surface area formula is that. Express the surface area as a function of volume. So basically what I would do here is we need to combine these two equations together basically. They both have a value of d in them. So what I would do is I would take this equation here, solve that for d, and then if I solve this for d, I can take whatever that d value is and plug it into this spot here. So I get it all basically as one equation. It's kind of like the Fogg-Off stuff, just not written like that. But I'm going to take this one here and solve for d. So v is equal to, what I got, pi d to the third over 6. So if I'm getting the d by itself, I would multiply by 6 first. So 6v is equal to pi times d to the third. Then to get rid of multiply by pi, divide by pi. So 6v over pi is equal to d to the third. Then to get rid of our power of 3, opposite of that would be like the third root of it. So that would be gone, that would be gone. So our d would end up equaling the third root of 6v over pi. And then what you're going to do is, now that you've found that d, you're just going to take that and plug that back into the surface area formula. So like surface area would be equal to pi, and then our d there, we're going to switch that out for cubed root of 6v over pi. And then technically you can do a little bit, oops, squared. Technically you can do a little bit of reducing down with this stuff, because like you could kind of combine this stuff together a little bit here. I'm cool if you just leave it like that though, because technically it is, you know, volume into that formula, so you can leave it like that and be fine. Like I said, I'm not too worried about these couple sections. I just wanted to review a little bit on some of the power stuff. So I'm going to have you guys do a worksheet